In a spatial relativity, we have discussed in very detail a very important set of transformation equations which are actually called the Lorentz transformations. And you know, actually these Lorentz transformations are the basic equations on which the complete spatial theory is based on. But I have not discussed two very important type of Lorentz transformations which are called proper Lorentz transformation and improper Lorentz transformation. So a large number of viewers of my channel have demanded me to provide a short video on proper and improper Lorentz transformations. Okay. So for seeing the need of such viewers, I would like to provide a video on it, and that will be discussed in this present lecture. Okay. You have an idea of Lorentz transformation because I have already provided a video in the playlist of a spatial relativity of my channel, and I hope definitely who have demanded such a video definitely have watched my video on Lorentz transformation. Okay. So when you have watched the Lorentz video on Lorentz transformation and studied in your textbook, definitely you have an idea that these Lorentz transformations are what? These are actually the transformations which describe how the space and time coordinates change between the two inertial frames moving relative to each other. As you can see in this figure, I have considered here two inertial frames. One is S and another is S dashed. Okay. I have shown that the x-axis of both of these frames are coinciding. It is not necessary, but I have shown in this figure. Okay. And these two frames are in relative motion. And for simplicity, I have shown in this figure that the inertial frame S dashed is moving with a constant velocity v in x direction relative to S. So velocity of S dashed is v relative to S in x direction. So you can also say that velocity of frame S with respect to S prime will be minus v, that is in negative x direction. Okay. So actually these two frames are in relative motion. The aim of Lorentz transformation is what? As I have told you, that if you know an event in frame S, how we can find that event in frame S dash, that is the aim of Lorentz transformation. And you know, when you talk about an event in mathematics or physics is described by the space and time coordinates. For example, I have shown in this figure that at this point P an event is taking place. And an observer of frame S situated, let us say, at the origin O of the reference system S describes that event in this way: x, y, z, t. It means in frame S the event takes place at a point whose space coordinates are x, y, and z, and the time at which that event takes place is t. But when the same event is observed by the observer O prime of the frame S dashed, the specification of the same event by that observer is x dashed, y dashed, z dashed, t dashed. Okay. How these x dashed, y dashed, z dashed, t dashed depend on x, y, z, t, that is actually furnished by Lorentz transformation. Okay. So I have told you that Lorentz transformations describe how space and time coordinates change between two inertial reference frames moving relative to each other. Okay. In fact, these transformation equations you have learnt have been obtained on the basis of the second postulate of spatial relativity. And according to the second postulate of spatial relativity, the speed of light or any electromagnetic wave in free space is an invariant, is an absolute constant, having the value 3 into 10 to the power 8 meter per second. So also we know from spatial relativity that a space-time interval is also invariant. A space-time interval and the speed of light in free space, both are invariant. So taking these two invariant space-time and speed of light in free space under account, Lorentz have derived the transformation equations. Basically, when you have studied the Lorentz transformation equations in my earlier videos, you have seen that in matrix form these transformation equations are given like this, which I have defined here. Okay. Here in this column matrix in RHS are actually the specification of the event in S frame, and the column matrix in the LHS is the specification of the same event in the frame S dashed, which is in relative motion with respect to the frame S. If you consider that the frame is moving in X direction, actually in that condition this transformation equations hold. Okay. Actually this 4 by 4 matrix which I have marked here, this is actually called the Lorentz transformation matrix. When this matrix is operated on the column matrix Ct xyz, then we obtain the column matrix Ct prime x prime y prime z prime. You can see C is invariant, it is same in frame S and in frame S dashed. Okay. Here actually when you write beta, that beta stands for V over C. Okay. And gamma, this is actually 1 over root over 1 minus beta square. This is actually called Lorentz factor. This gamma is known as Lorentz factor. Okay. This is called Lorentz factor. Okay. All these facts you have already discussed in my previous video, and as I have told you, the aim of the present video is to provide you the idea of proper Lorentz transformation and improper Lorentz transformation in nutshell. Actually this is a vast subject, but I have provided the material in a very liquid manner, in a very short form, so that you will be able to write the answer of your question in your examination in very easily. Okay. So now let us talk about Lorentz transformations. Proper Lorentz transformations. Actually, proper Lorentz transformations are defined as a transformation having determinant equal to plus 1. Mark this. Those Lorentz transformations whose determinant is plus 1, such Lorentz transformations are called proper Lorentz transformations. Actually, these proper Lorentz transformation actually preserve the orientation of space and the direction of time. Okay. It means when you talk about the proper Lorentz transformation, the orientation of the space coordinates do not change, and the direction of time also do not change. Okay. So this is the most remarkable property of this proper Lorentz transformation, that in this case the orientation of space and the direction of time both are preserved. Okay, both are not affected, both are not changed. Okay. Now let us see two most important examples of this proper Lorentz transformation. First one is called boosts. When you talk about boosts, what are actually these boosts? In fact, these boosts are the transformation of space and time coordinates when relative velocity between two inertial frame is along an axis. Actually, in my previous video on Lorentz transformation, we have actually derived this boosts, because when you basically talk about Lorentz transformation, then you actually transform the space coordinate of the event and the time coordinate. And you also consider that our coordinate system is, our reference frame is moving in the direction of a particular axis. As you can see in this figure, I have shown here that this frame S dash is moving in x direction. So actually, when the relative velocity is in the proper particular axis, let us, for example, if you consider that the relative velocity of the frame is along the x-axis, in that condition, the space coordinate and the time coordinate both will be transformed. Okay? And such transformations are called boosts. Such transformations are called boosts. I have actually derived the results for this transformation in my previous video. So I have written this transformation directly here. You can see x dashed is given as gamma times x minus Vt. And you know, gamma is given by 1 over square root of 1 minus beta square. So x dashed is equal to x minus Vt over a square root of 1 minus beta square. Okay? But beta, you know, this is V over C. So instead of beta square, you may write V square over C square. So in this way, you can write the transformation equation for the x coordinate. So if you know the x coordinate of the event in frame S and the relative velocity between the two frames, then you can find what will be the x coordinate x dashed of the same event in frame S dashed. Okay? Now, when the frame S dashed will move along the x-axis, then the y and z coordinate of the event will remain unaffected. So y dashed is equal to y and z dashed is equal to z in this case. But the time coordinate gets changed. The time of the event taking place was measured by observer O, and he claimed that time is t. But when the same event is observed by the observer of moving frame S dashed, then he measures the time of event as t dashed, and t dashed is not equal to t, but it is equal to gamma times t minus v over c square times x. Again, instead of this gamma, you can write 1 over root over 1 minus beta square or square root of 1 minus b square by c square. So t dash is given as t minus v over c square x over square root of 1 minus b square by c square. Now, I have actually written this result in matrix form here. This is the matrix form of this transformation equation. And you can check that the determinant of this Lorentz transformation matrix, when you will find, that will be equal to 1. You can check the algebra. Okay? So these boosts are actually the example of proper Lorentz transformation. Another important example of proper Lorentz transformations are rotations. Okay? Actually, when you talk about rotations, these rotations are actually the linear transformation in the physical space. linear transformation of physical space. So when rotation transformations takes place, then there is a change in the spatial orientation of the reference frame. A spatial orientation of the reference frame. But time coordinate remains unchanged. So you can see, if we consider that about the z-axis, the reference frame S is rotated, then its x-axis is rotated to the position x dash, y-axis is rotated to the position y dash, let us say by angle phi, okay, by angle phi, okay. I have shown here minus phi because a sense of rotation has been shown in opposite direction, okay. And this rotation has been carried about the z-axis, so I have not shown the z-axis, because if rotation will be carried about z-axis, z-coordinate of any point will not change, okay. But let us say P is a point whose coordinates are x, y, z, t in frame S and x prime, y prime, z prime, t prime in frame S prime. Then if the angle of rotation is phi, then you can see from this figure that actually the x and y coordinates of point P in frame S are x and y, and the same coordinates in frame S dash are x prime, y prime. And I have shown the perpendiculars from point P on the x-axis and y-axis. So the length of these perpendicular actually represents the y coordinate and the x coordinate, okay. Similarly, I have also drawn perpendicular from point P on x dash axis and y dash axis. So this length of this perpendicular is y dash and length of this perpendicular is x dash. Now from the geometry of figure, you can easily find, I have not explained that, but you can do the algebra. This is just a homework for you. When you will try to find x dashed, that will be equal to x times cos phi plus y times sin phi. And y dashed will be minus x sin phi plus y cos phi, and z dashed will be equal to z because rotation has been carried about the z axis, okay. Now you can write these equations in linear, and for time you can write t dashed equal to t, okay. So in matrix form, when you will write these four equations, what will be that? That will be a column matrix or column vector x dash, y dash, z dash, t dash, and that is equal to this Lorentz transformation matrix, which is a 4 by 4 matrix. You can see operated on the column matrix x, y, z. You can check when you will operate this transformation matrix. This is transformation matrix, TM, transformation matrix, Lorentz LTM, Lorentz transformation matrix. When this will be operated on X, this column matrix, you will get the column matrix X prime, Y prime, Z prime and T prime. Okay. So here you can see that orientation of the coordinate axis has been changed, but there is no change in time. And this is the effect of the rotation transformation. And it is a very good example of the proper Lorentz transformation, because when you will find the determinant of this Lorentz transformation matrix defined here, you will see that its determinant will be equal to plus 1. And that's why this is called a proper Lorentz transformation. Okay. So after these two very good examples of proper Lorentz transformation, I think you have a clear-cut idea of the proper Lorentz transformation. Now we will see in nutshell the idea of improper Lorentz transformations. You have seen that if the determinant of the Lorentz transformation is plus 1, then it is called proper Lorentz transformation. Here you have to say, if the determinant of the Lorentz transformation is -1, then it is called improper Lorentz transformation. So I have mentioned here that improper Lorentz transformations have a determinant of -1. Okay. Now let us see again the two most important examples of this improper Lorentz transformations. First one is a space inversion, or you can also say a spatial inversion, okay, or parity transformations. You have definitely studied this parity, concept of parity in nuclear physics and in quantum mechanics. Okay. Actually, what is this space inversion? Actually, a space inversion is the operation in which the axes of the reference frame are reflected at the origin. You can see this figure. This x-axis now becomes x-dashed axis, y-axis becomes y-dashed axis, and z-dashed axis becomes z-dashed axis. So, this is the operation in which the axes of the reference frame get reflected at the origin. And therefore, the effect of this operation is to change the right-handed coordinate system into the left-handed coordinate system, and the left-handed coordinate system into the right-handed coordinate system. Okay? So you can say that the parity transformation flips the sign of the space coordinates, leaving the time coordinate unchanged. In this case, only the sign of the space coordinate get just reversed, but sign of time coordinate remains same. So, in nutshell, you can say that parity transformations are the transformations of flipping of the sign of a space coordinate without the flip of direction of time. Okay. So this transformation is written like in this way: x dashed is equal to minus x, y dashed is equal to minus y, z dashed is equal to minus z, but t dashed is equal to t, not minus t. Okay. Now again in matrix form you can write these transformations in this way. See here. The column matrix x dashed, y dashed, z dashed, t dashed is equal to this Lorentz transform. This is Lorentz transformation matrix. Okay, LTM, or which is actually the parity transformation matrix. We can see, and when it is operated on this column matrix x, y, z, t, then you get this column matrix or column vector. Okay, again you can check. When you will find the determinant of this transformation matrix, which is a 4 by 4 matrix here, you will get that its determinant is equal to -1. That will be not +1 but -1, and so that it is an example of an improper Lorentz transformation. Okay. Now, another very important example of improper Lorentz transformation is time reversal. Okay. Actually, when you say time reversal, actually in time reversal operation, the time is reversed. It means t becomes minus t, but there is no effect. In this case, the velocity changes in sign, but the position coordinate is not affected. This is a very remarkable fact. In time reversal operation, velocity changes its sign, whereas the position coordinate is not affected. Okay. So, I have mentioned here that in time reversal operation, the direction of time is reversed, but the spatial coordinates remain unchanged. Although a spatial coordinate remains unchanged, but if an objective question will be asked if there is a time reversal operation or time reversal transformation, the sign of velocity changes or not, answer will be yes. Sign of velocity is changed, but sign of the space coordinate do not change. Okay? It means that this transformation flips the arrow of time only, not the sign of position coordinates or space coordinate. Therefore, you can easily write this transformation in this way: x dashed is equal to x, y dashed is equal to y, z dashed is equal to z, and t dashed is equal to minus t. So you can see this is just the reverse of the parity operation. When you parity operation, you can see in parity operation the sign of a space coordinates is changed, but sign of time coordinate do not change. But in time reversal, sign of a space coordinate do not change, but there is a flip of the arrow of time. Okay, so this is just the reverse process of the parity. Okay, so again this transformation in matrix form you can write like this. You can check it. Okay, when you will multiply this 4 by 4 matrix to this column matrix, you will get the column matrix given in the LHS. Okay. Again you can see when you will find the determinant of this 4 by 4 matrix, which is actually the time reversal matrix, then you will see that its determinant is equal to -1. And that's why this time reversal transformation is known as an improper Lorentz transformation. Okay. Now actually these improper transformations are not continuously connected to the identity transformation, unlike the proper Lorentz transformation. Actually proper Lorentz transformation is continuously connected to identity transformation. You have studied the identity transformation in matrix formulation of quantum mechanics. Okay. But these improper transformations are not continuously connected to the identity transformation. Actually, in summary, we can say that the proper Lorentz transformations form a continuous group. Mark this. This is a very important question for objective type question. So, proper Lorentz transformation forms a continuous group, while improper Lorentz transformation involve discrete operations that are not continuously connected to the identity. Okay, so I think this brief lecture has definitely clarified your idea about the proper and improper Lorentz transformation. Okay, thank you very much.